Alright, in this section we're going to be looking at, this is 25C, if you're following your book it's page 530, we're looking at the derivative function, which is simply a way for us to find the tangent, or find the gradient of a tangent at any given value for x without having to go through the entire long process. So the derivative function is also called the gradient function, and we called it the derivative function because it's derived from whatever f of x is. So we write the derivative. If we have f of x, we would write the derivative of this as f prime of x. So let's walk through the long version, and then we're going to talk about the short version on how you would solve this. So if I'm finding the derivative, we know that I have, first of all, I have my generalized point f, which is x, and the function of x. I also have point m, which is x plus whatever h is, and the y value would be the function of x plus h. Now I use from here my slope formula, and I'm going to get f of x plus h minus f of x over x plus h minus x. And of course those two x's will cancel out, so I'm really left with just h in my denominator. And the cool thing is that this is a formula that you can use anytime in any situation to find the derivative. So we would say the limit, I don't know why I just wrote an h there, but the limit as h approaches 0 is this thing. Okay, so there we go. Now, let's take that and let's use it on one. So, for example, we're using f of x equals x squared. This is our parent function. Then we can use this and we can say f prime of x equals the function of x plus h. So we take x plus h and we plug it in here, and that's going to give us x plus h squared. And then we take x and we plug it in here, and that's going to give us x squared, so this is minus x squared over h. So work this out. We get x squared plus 2xh plus h squared minus x squared over h. These two will cancel out, which leaves us then with 2xh plus h squared over h. Let's go ahead and factor out an h, and we get 2x plus h over h. We have another cancellation, so we're left at the very end of things with 2x plus h. So we would say then a couple of things. We would say the limit as h approaches 0 of 2x plus h. Let's plug in 0 for h, and our solution is 2x. Now, the way we would read this is f prime of x equals 2x. And we saw that to be true the other day by looking at the different points on x squared, the function of x squared, and we said that when x is 1, the gradient was 2. And we said when x was 4, not 4, 2, then the gradient was 4. We said when x was 3, then the gradient was 6. And it just kept going up, and we found that this was the pattern. 2 times whatever the value x of x was the gradient of the tangent at that given point. So hopefully you can see from that how this derivative function is going to be really, really helpful and save you a lot of time. Now, I'm going to save you even more time. If you're following your book, it's page 534 at section D. That's the long way of working out the derivative function. There's a much shorter way, and that is just learning the rules for differentiation. Remember, differentiation is when we derive the derivative function. And we say we're differentiating from first principles if we use the limit theory to do so. So the general rules we need to understand is that when we have f of x, f prime of x for any constant or c is always going to be 0. Basically, we drop them. Another rule we look at is x to the n power such that n is not equal to 0. Essentially what we do here is we take this exponent, bump it down here, and then the remaining exponent will be n minus 1. So what that would look like if we wrote it out as a formula would be n times x to the n minus 1 power. Now, from here, we can, if we're looking at a function and it has either multiple sums or terms being added or the difference, we just essentially work piece by piece and use these rules to find the derivative. So let's do an example one. We want to find f prime of x if f of x equals x cubed plus 2x squared minus 3x plus 4. So again, we have the sum here, and so we're just going to take this thing piece by piece and see what we can come out with. So let's take our rule. We're going to bump this exponent down, and then we're going to subtract 1 from it. So when we bump it down, it gives us 3, and then 3 minus 1 gives us 2. This is the derivative of x cubed. Let's do the next piece. Same process. Bump that 2 down. That gives us 2 times 2, which is 4. And subtract 1 from it, which is x to the first. Do it one more time. So here's our understood 1. So let's bump it down. And we get negative 3 times 1, which is just negative 3. Now, the trick here is, in my exponent, when I subtract 1, I'm going to get 0. Well, x to the 0 power, any number to the 0 power is just going to be 1. So I'm left then with negative 3 times 1, which is negative 3. And remember, we said that our exponents are going to drop or turn to 0, so we pretty much don't need those. So this is the derivative function of this thing. And let's look at one more example quickly. We have f of x equals x plus 4 over root x. Now, the first thing we need to do is we need to take this x, so this root x, and we need to get it out of the denominator. So to do that, we're going to change that from root x to x to the 1/2 power. And then let's move it up into the numerator, and we're going to get, when we do that, this becomes x to the negative 1/2 power. And let's distribute that. So when we distribute here, we should come out with x to the 1/2 power plus 4x to the negative 1/2 power. And then we can work from there, and we're going to follow the same process where we bump this down in the front, which gives us 1/2 x. Subtract 1 from it, so that's going to give you negative 1/2. Same thing here, this will give us negative 4 over 2, which is negative 2 to the x. Subtract 1 from it, and that'll give you the negative 3/2. And we should be able to finish things out from this point.